So what is partial correlation, and how can we use simple techniques in R to learn more about it? Stick around and let's find out. Hello and namaste. My name is Brandon and welcome to the channel. Now on this channel you will find lessons and tutorials for statistics, data science, and related fields. That can help you get higher grades in your class, prepare you for that next job, or just sort of quench the natural curiosity you might have around these topics. Now when all is said and done, if you like the video, please give it a thumbs up, share it with classmates, colleagues, or friends, or others you think might benefit from watching. And of course, if you haven't already, please hit that subscribe button and the bell notification. Now in the description below, you will find two important links. One is to sort of a table of contents for all of my videos. So if you want to study something else, just follow that link and you'll see that table of contents there. The second link goes to where you can download the files to follow along with this video. So again, look for those in the description below. So now that we are introduced and up to speed, let's go ahead, hop into R and learn about partial correlation. Now I want to reiterate that you do not need to have advanced knowledge of R to watch this video. In fact, I'm going to assume you know very little. Now, many of my users have quite a bit of R experience, whereas another subset of my users do not. They are typically just business students or university students that are taking a stats class for their major or just for their general requirements. So I'm going to assume a low level of R knowledge. And actually, we are only going to stay in the RStudio interface here for a few minutes. We will hop out to an HTML file created from this RStudio environment and then follow along with the actual lesson in the video. When it comes to this R environment that we have here, I'm running an R project. So an R project kind of has all of your stuff in one place. Now the file that you see over here on the left is actually an R notebook. It's very similar to the Jupyter notebook you might see when using Python. And the language inside this R notebook is called R Markdown. So you can see the hash signs. So the one hash is actually an H1 heading, two hashes is H2, and so on and so forth. So if you want to know more about how this document is put together, just do a Google search or YouTube search for R Markdown or R notebooks. And of course, you can download this project file as a zip in the link in the description below. Finally, and very quickly, what makes this R notebook environment so flexible is that you can run chunks of code. So here in this load library chunk right here, on the right, you'll see a green arrow that looks like a play button. So if I hit that play button, what it will do is execute this chunk of code. And then I could go down to the next chunk, which you would see down here. So if I click this button, it will load in a data set we have up here on the right. And then it also opens the help file for the data set we are using. That's the second line of this code chunk. So you can see that R notebooks are pretty cool. They allow you to run your code in chunks. You can, using R Markdown, put in instructions and images, which we'll see, and so on and so forth. But I don't want to go into all that here. I just wanted to kind of explain how this is all put together. So what I'm going to do is go up to this knit button. What that will do is allow me to create an HTML file based off this R Markdown in the notebook. So I'll hit knit to HTML. It will run that. And the first thing it does is it opens our mtcar dataset help. That way we always have that available. Now if I go down here, another window opened up. This is the browser inside of R, but I want to make this even bigger. So I'm going to open it in my actual browser. And now we have everything blown up nice and big. So let's go ahead and actually get to the meat of the video, which is partial correlation. So first things first, I have all my YouTube resources up here at the top. So my main channel, all my playlists, this playlist that we're in right now, which is model building, playlist 20, and then the previous video in this playlist, which is a visual guide to partial correlation. And I do recommend you watch that before doing this one. So when we go into the numbers and do all the regression models and stuff, you'll actually know why we're doing them. To understand the gist of this video, what should you know to start with? So basic statistics like correlation and linear regression. You should know what the R-square is in a regression model. You should know what residuals are in a regression model, because they will play a very important role in this video. And it will help, like I said, if you've watched the previous video that I've listed up here above. So the first thing we have to do is load in libraries for R. So those are add-ons to R that extend its functionality and make some things easier to use. So we may not need all of these libraries, but they're good to have handy. If we were writing super optimized code, we would be meticulous about package management, but for this small example, this is fine. Now, I also want to note here that I am not an R expert, and this is not a tutorial on R. There are many ways to do the same thing in R, and probably many of you watching this are much better at R than I am. So I just want to get it out of the way that I'm using R here as a tool, not as like teaching people how to use R. And I've kept everything very simple. So what I do here is strictly for teaching purposes. So just sort of keep that in mind. So we load our libraries in. Datasets are the built-in datasets that are in R. Knitter is what we use to create this HTML document. ggplot2 creates plots. Psych is a fantastic package for statistical analysis. It is massive. It has all kinds of tools in it. It's well supported. So I definitely recommend you learn more about Psych if you have not learned about it already. And then LM support is a package that helps with linear models. So LM, linear model support, and it gives us some additional functionality we'll use towards the end. So those are the libraries that we will pull in. Next, we will load in the mtcars dataset. So mtcars is a very famous dataset that's built into R. You'll see it used in many tutorials and books and things you might read. So we will stick with that. And most of us are familiar with how cars work, so it's also practically useful. So we'll load in mtcars into a data frame. So an R data frame, if you're not familiar, is sort of similar to an Excel spreadsheet. Of course, there are differences, but if you're looking for something that's analogous to your everyday experience, an R data frame is similar to that Excel spreadsheet. So it's easy to understand the structure of named columns and rows of observations and so on and so forth. So what we'll do here is we will take the mtcars dataset and then we will assign that using this sort of arrow operator to another object called dfcars. So we're telling R, hey, take the mtcars dataset and put it in this object named df_cars. And then the second line will open up, like I showed you before, the help file for the mtcars dataset that shows you what the data actually is. So if I go over here, let me make this a little bit bigger. So you can see where the data comes from. It's from 1974, a Motor Trend magazine. Looks at 10 aspects of automobile design for 32 cars. This lists all of the variables that are in the data set and then their position within the columns. So MPG is the first variable, number of cylinders, second variable, so on and so forth. That can be very handy when you're trying to just work with certain variables and any notes and things like that. So that's what this little line here does, is it opens that help file for you. So the next thing we do is we're going to do some initial correlations just to get a feel for our data set, get a sense for it. So this is simple exploratory data analysis. Now we want to pay special attention to the first column in this correlation matrix, which is miles per gallon. That's going to be our overall dependent or target variable. So we are particularly interested in that variable. So to generate this plot, we use the core plot. So core.plot mtcars. That will give us our full correlation plot. And this is what that looks like. So you can take a look at that for a second, pause the video if you want. And again, we're interested primarily in this first column with MPG. Now, a few things we should keep in mind. So we can see that the variables with the strongest negative correlation with miles per gallon are cylinders, so number of cylinders. We can see that here at negative 0.85. Engine displacement, which is negative 0.85. Horsepower, car weight, and number of carburetors. Number of cylinders are just like you've heard terms like V8, V6, flat 4, stuff like that. Those are just the number of cylinders in the car. Displacement is sort of the volume of those cylinders. So if the displacement is larger, the volume inside those cylinders is larger, and that allows more fuel to be burned. Engine horsepower, I think we all know what that is. Car weight, obviously just the weight of the car. And then back in the 70s, engines used carburetors, which basically pull in and mix the air and fuel. Now nowadays, we primarily use fuel injection, but carburetors were sort of the fuel injection of 30, 40, and longer years ago. Now, this should all make sense because all of these contribute to using more fuel and therefore should logically tend to have a negative correlation with miles per gallon. So, number of cylinders, that means more fuel can be burned. Larger displacement, that means more fuel can be burned. Therefore, miles per gallon would be negative. Horsepower, more powerful cars tend to burn more fuel. Therefore, miles per gallon is negative. Heavier cars tend to burn more fuel. Again, so on and so forth. Now, the variables with the strongest positive correlation with miles per gallon are DRAT, which is the rear drive gear ratio, quarter second, which is the quarter mile time in seconds. So if you've ever seen like a drag strip or a drag car race, we have those here in the US. I'm not sure where overseas you might have those if you're watching this overseas, but the car just is at a standstill. The light turns green and the car goes. It just goes as fast as it can for a quarter of a mile. And then we time how long that takes. VS is the shape of the engine. So some engines are in a V shape. So you've probably heard of a V8 engine or a V6 engine. Some engines are inline. Some engines are flat. So my car has what's called a boxer engine and a Subaru. So the engine is flat. So VS is just shape of the engine. AM is automatic or manual transmission. So a manual transmission you're probably familiar with. It's the gears, usually in a stick shift in the console middle of the car. And then gear is the number of forward gears. A lot of automatic transmissions are 4-speed transmissions. My car is a 5-speed transmission. Other cars maybe have 6-speed transmissions and gears. So that's what we mean by gear. And if we go up, those are all positively correlated with miles per gallon. So if a car has a higher, or what we call a taller gear in the rear end, that usually means that for the wheels to spin, the engine turns less. And therefore, if the engine's turning less, you're using less fuel. Quarter second time, that makes sense. Cars that are slower in their quarter second time tend to be less powerful and therefore use less fuel. And of course, actually, if we take a look over here, we can see that quarter second time has a strong negative correlation with horsepower. That tells us that higher horsepower cars have lower quarter second times and vice versa. Automatic and manual, that's the gearbox. So if we go down here, we can see that one is manual. So manual cars with a stick shift tend to get better gas mileage actually. And then number of gears, again, like I said, if you have more gears, that allows the engine to run more efficiently. So those are our two sets here. So these first sets tend to decrease miles per gallon, and this other set down here tend to increase miles per gallon. Next thing we'll do is go for data frame preparation. So what we're going to do for this simple example, we're just going to focus on one independent variable, miles per gallon, and just two of those independent variables. So DRAT, which is the rear end gear ratio, and then horsepower. So we're just looking at those two variables out of all the ones above. We are interested in the partial correlation between miles per gallon and DRAT while controlling for the effect of horsepower, and the partial correlation between miles per gallon and horsepower while controlling for the effect of DRAT. So we are going to conduct two partial correlations while controlling for the third variable. Therefore, let's create a data frame that just has what we need. So let's scroll down a little bit more. So this code creates a list of three variables we want to keep and then places them into a second smaller object or data frame here. So it's a subset of the larger MT cars. So we'll call this variable here, or this object keeps, and we will assign to that a list of the variables we want to keep. So miles per gallon, DRAT, and horsepower. Now keep in mind the quotes here, and they have to be spelled exactly the same, including capitalization. So MPG, DRAT, and horsepower. Then we create a second data frame, so DF cars 2, and we assign to that MT cars, which is our larger data set, but just the three variables we listed above. So go into MT cars, get just the variables that we listed out in keeps, and put that into a second data frame called DF cars 2. Now, to make everything clear, we will place each variable into its own object, so we have explicit names for each variable. This will also allow us to manipulate each variable easily. Technically, you do not have to do this, but I'm doing this again just for teaching purposes. So we're taking the first variable here, empty cars, then the $, and then miles per gallon. So we're telling R, go into the empty cars data set and grab the column or the variable of miles per gallon, then assign that to a object here called y_cars, because that's going to be our overall dependent variable, target variable. Then do the same thing for drat. We're going to assign that to a variable x1_cars, and then horsepower x2_cars. So we have our y, x1, and x2. We next need to create some basic linear models and then place the models into objects. So the first listed variable after the lm command, which you see here, means linear model, is the target of that model. And the variables that follow this tilde sign are the independent variables we are putting into that model. So a consequence of this step is that we will also obtain the important R² values we used in the previous video. So let's look at these one by one. We are creating an object called cars_yx1, and we're going to assign to that this linear model. So lm, then we have y_cars, that in this case is our target variable, tilde, and then x1_cars, that's our independent variable. So here we are doing a simple regression model of using x1 cars, which is also drat, remember, by the way, to predict the miles per gallon for the cars. Then below that, we do the same thing, but for horsepower. So now it's x2. So we have y_cars and then x2_cars. Then the next two might seem a little bit odd, but we need these to get residuals. So in these next two, we're actually taking the independent variables and regressing them with each other. So in this first example, x1 is the target variable. Remember, that's drat, and then horsepower is the independent variable here. Below that, we flip them. So x2 is the target variable, that's horsepower, and then x1, which is drat, is the independent variable. And then below that, we have the full model. So y, x1, x2. So y_cars regressed with the independent variables of x1 cars and x2 cars. So we have two single variable regressions, two regressions where we're regressing the independent variables overall with each other, and then we have the full model down below. So this will give us all of our R². It will give us residuals that we will need here in a minute. So very quickly, here are our model summaries. We actually did this in the previous video, but I just want to show you the output so you can kind of see where to find it in R. So the summary.lm function gives us all of this information. So if you ever create a linear model and you want to get, the residuals, you want to get the coefficients, the significance values, and then all of the, standard errors and stuff like that, just use this summary.lm function. So we can see on here this multiple R² of 0.464. That's the same thing we found in the previous video. So when we regressed drat with miles per gallon, we got an R² of 0.464. So we'll keep scrolling down. So here's the same idea, but with horsepower. Our R² here is 0.6024. Again, that's the same value we found in the previous video. Now, when we regress the independent variables on each other, we're actually going to get the same R². However, the residuals will not be the same. They're related, but they're not the same. Here is the R² of 0.2014. Same thing down here, 0.2014. Now our full model with miles per gallon as the target or dependent variable, and then our two independent variables together simultaneously, we have the multiple R² of 0.7412. And again, that's the same R² we found in the previous video. So we just did a series of simple regressions, linear regressions, using the lm function and the variables we created from above. Next, we need to capture the residuals, because under the hood, partial correlation is actually about the correlation among residuals. That's why we're grabbing them. So all we are doing here is taking the 5 regression models we did in the step above, and then grabbing the residuals using this function here, resid. So if we do resid, then we put in our first regression model, we can assign those residuals to a different object over here, and we just call it cars_yx1 resid. So we're just grabbing the residuals off that model and putting them in their own object. And we do that for all 5 models. So miles per gallon and horsepower here, the 2 independent variables regress with each other, and then the full model. So now we have 5 sets of residuals. So now the partial correlation part. So think of it this way. I want you to put this question in your mind in this fashion. What is the variable we want to partial out? So if we're looking for the partial correlation in this case between miles per gallon and drat, what's the variable we want to partial out? Well, the answer is horsepower. So what is the implication of that? Well, horsepower will be the independent variable, and miles per gallon and drat will be the targets for 2 regression models. And again, you'll see how that looks here, obviously, in a second. To get the partial correlation between miles per gallon and drat, we need to take out the effect of horsepower. Now, regression is how we take out the effect of horsepower. So once we do that for both miles per gallon and drat, we have 2 sets of residuals, i.e. what's left. So think about that. To get the partial correlation between miles per gallon and drat, we take out the effect of horsepower. Regression is how we take out the effect of horsepower. Remember, we're going to grab up all the variance that we can using these regression models, and then we're going to have residuals, i.e. what's left. Now, the correlation between what's left is the partial correlation between miles per gallon and drat. And as a diagram, it looks like this. So we have 2 simple regressions here. On the left, we have the 2 variables we want the partial correlation for. So in this case, it's miles per gallon and drat. Then what we're going to do is create 2 regressions with the variables we want to partial out, which is on the right. So in the second box here, we have the variables to partial out of the 2 variables on the left. Then from those regressions, and again, we can have more than 1 variable. Here we just have horsepower, but if we were doing partial correlations with the entire MT cars data set, and we wanted the partial correlation between miles per gallon and drat, we would put all of the other variables to the right of that tilde sign, and then we would still get the same residuals and so forth. So we have 2 regressions, and then we get 2 sets of residuals out of those models. Then we do the correlation between those residuals. That gives us the partial correlation between the 2 variables that we were interested in the first place. In this case, miles per gallon and drat. See how that works? So this means 2 regressions where horsepower is the independent variable and drat and then miles per gallon are the target variables respectively. So we already did this actually. So this is actually repetitive code. I just put it down here again, so it's with this diagram. So we create our 2 linear regression models. Then we grab the residuals off those 2 linear regression models. And then we go down here, and what we do is we create an object. So here, parkour underscore mpg underscore drat. We're going to assign to that the correlation between those residuals. So what we're doing here is 2 regression models, grab the residuals. Now we're doing a correlation between those 2 residuals, and then we print it out. So in this case, the partial correlation between miles per gallon and drat is 0.5907. So you see how that works? Partial correlation is a correlation between 2 sets of residuals. Now, that was 0.5907301. Now, the bivariate correlation that we did at the very beginning with all of our variables was 0.6811719. So we can see that the partial correlation is quite a bit lower than the bivariate correlation we had above. And we'll talk about what that means in the grand scheme of things here in a few minutes. Now next, we have the partial correlation between miles per gallon and horsepower. This is the exact same process. Again, think in your mind. Question to ask, what is the variable we want to partial out? In this case, the answer is drat, because that's the one that's not in the 2 variables that we want to get the partial correlation for. So the implication is that drat is the independent variable, and then miles per gallon and horsepower are the targets for our 2 regression models. So to get the partial correlation between miles per gallon and horsepower, we got to take out the effect of drat. And again, regression is how we take out the effect of drat. We go in and we use the models of drat to miles per gallon and drat to horsepower to grab up all the variance that we can in each of those 2. So once we do that for both miles per gallon and horsepower, we have two sets of residuals, i.e. what's left. And again, the correlation between what's left, the residuals, is the partial correlation between miles per gallon and horsepower. So the diagram looks like this, similar to above. So we're interested in the partial correlation between miles per gallon and horsepower. We'll create two regression models where drat is the independent variable. We get two sets of residuals. We correlate the residuals. That gives us the partial correlation of miles per gallon and horsepower. So this was the same process. I'm not going to go through this in detail, but we have our two regression models, our two sets of residuals. We correlate the residuals and print it out. So the partial correlation between miles per gallon and horsepower is negative 0.7191. And the bivariate correlation we had at the very beginning was negative 0.7762 approximately. So you can see here that the correlation didn't change as much from the bivariate correlation in the beginning to the partial correlation here. So it would appear that the relationship between miles per gallon and horsepower, at least in this scenario, is stronger because the effect of drat was minimal. As compared to the first situation where when we used horsepower as the independent variable, that lowered the bivariate correlation of drat to miles per gallon a little bit more. So I think it went down to like 0.59 or whatever it was. Yeah, 0.59. So it appears here that the relationship between miles per gallon and horsepower is stronger, or at least it's not affected by drat as much as the reverse. So two more steps here that can make this a bit easier in the long run. We went through all that during this video to show you conceptually what's going on actually, so you know what's actually going under the hood, because my videos are largely about conceptual, not just copy some code and paste it and there you go. So I want you to understand what's actually going on. So we can use the psych package for sort of one-stop shopping. The psych package has a partial.r function, and it has something called lower mat, which actually makes our correlation matrix look prettier. So we can use this command here. So we have inside, we have partial.r of our df underscore cars2 data frame. Remember, that's the data frame we created at the beginning that has just our three variables. So that's why we needed that here. So partial r of that data frame, and then put it inside this lower mat, which makes it easier to read. So if we look here, this is what we get. So first, lower mat makes it easier to read. If you notice here, we only have sort of this wedge shape because everything above that is repeated. That's what lower mat does, gives us the lower mat of all this output. And then partial r, of course, gives us our partial correlations. Now, if you notice, these numbers look familiar. So the partial correlation between miles per gallon and drat was 0.59. That's exactly what we got above. And then the partial correlation between miles per gallon and horsepower, which is what we just did right here, was negative 0.719. It rounds it to negative 0.72. So that is a one-stop shopping command inside of the psych package that you can use to find partial correlations. And finally, there's a package called LM support, so linear model support, and I misspelled that, my apologies. Now note that this takes in the full model, so both of our independent variables, and then produces partial eta squared, or the effect size values, for which the variance associated with the effector variable. Now, we could go into effect size and do a whole other video on that, which I probably will at some point, but I'm just kind of explaining what output it gives you and how you have to interpret it to get the partial correlations that we're interested in. So therefore, you will have to take the square root of the partial eta squared to obtain the partial correlation. If you look down here, we're going to use this command model effect sizes, and then we put in our full model. And down below, we get this partial eta square column right here. So this is our effect size. Partial eta squared, this column here, is effect size, and it's the percentage of the variance in the dependent variable explained by the independent variables in the sample. So how to interpret that is that X1 cars, which is drat, explains about 35% of the variance in miles per gallon, and then X2, which is horsepower, explains about 52% of the variance in miles per gallon. Now notice that these are squared. So if we take the square root of these values, then we get our partial correlations. So the square root of 0.3490 is 0.5901, which is the partial correlation between miles per gallon and drat. And then the square root of 0.5171 is 0.7191, or in this case, it's negative, remember, because the correlation between miles per gallon and horsepower is negative, which is the partial correlation between miles per gallon and horsepower. So it's just a square root of the partial eta squared. So the square root of the partial eta squared is the partial correlation. Now this last column here is actually very interesting as well, and that's going to lead into our next series of videos, so I don't want to spoil that fun. However, if you look at those values, so 0.1387, 0.2772, if you remember from our previous video where we solved the Venn diagram puzzle, if you look, that's the value for A, so 0.1388, just because of rounding. So that's this area here in the purple. And then C, 0.2772, that's this area here in the yellow. And again, they show up here in this model effect sizes column here at the end. And we'll get into what that means a little bit later. And finally, just to reinforce that we're doing this the right way, all we're going to do here is create a correlation of all the residuals together. So I'm going to create a data frame, so data.frame, and then in that data frame, I'm going to put all the residual objects that we made. So yx1 residual, yx2 residual, and so on and so forth. Then I'm going to round those to 3 digits to make it easier to read. And then we get this little matrix down here, and you will see that these numbers reappear. So here is our negative 0.719, which is the partial correlation between, look what we're doing here, look at the variables. We have yx1, we have x2x1. Remember, the x1 is what we're partialing out. So this negative 0.719 is the partial correlation between y and x2, which is miles per gallon and horsepower. And then for the other one, is right here, so 0.591. Again, look at our variables we have stored. We're looking at yx2 and x1x2. So that's the partial correlation between y and x1 while partialing out x2. So 0.591 is the partial correlation between miles per gallon, which is y, and drat, which is x1. So we can see that again down here. All right, so that wraps up this tour de force of partial correlation using R as just a tool with some visuals to kind of see how everything flows together, some basic understanding of how R works, and then what's actually going on under the hood in partial correlation. So I hope you found this video helpful. I hope you find the files you can download and follow along helpful. And again, my information is here if you want to look at other videos of mine and this playlist and the table of contents for all my videos. But I will stop rambling now, and thank you very much for watching. I wish you all the best of luck in your future studies and in your work, and I look forward to seeing you again next time. Take care. Bye-bye.